teaching in 2023 is oddly complicated. All right, folks, nice to see all of you. I should make sure that this thing is actually recording. It is. Okay, welcome to day 3 of 6S955. I'm glad to see that we still have some people in the classroom. That's fantastic. So before we get started, a few announcements. First of all, remember on the syllabus, there's like a few pieces of this class. There are exams, homeworks, and then these little mini quizzes. I'm going to be honest, Chris and I forgot to write our quiz until today, so it will be posted during class, and I promise it will be the easiest quiz you ever took if you came to these lectures. I know, because we just wrote it. So I encourage you, if you came to lecture, to not study and just open it up and take it. We have set a 1-hour time limit. If you are finding yourself anywhere close to that time limit, then something has gone wrong, because it's literally 4 multiple choice questions that are basically regurgitating course material. Any questions about this? So we'll make it due Sunday night, since I think the deadline on the syllabus was Fridays, but just because we posted it kind of late. If you need that extra time, that's fine. But you should think of it as roughly the amount of time it takes to solve a Wordle. And remember that also in this class we drop the bottom 2 or 3 of them anyway. Basically, this is just a way to make sure you are responsible for the course content from week to week. Fantastic. And other than that, how many of us have started our homework? Fantastic, that's almost everybody. If you haven't, that's okay, because it's not due today. But I would encourage you to get started. So the homework is due next week, is that right? Next Thursday? Yeah. So it's time, and you have, as of today's lecture, you have basically everything you need to solve the homework problems. There were some people in my office hours yesterday, which is fantastic, and we just basically did the homework together. So for those of you who didn't come, you missed out on free homework answers, which is too bad. You left me lonely, and that's what you get. But in any event, lucky for you, Chris also has office hours every Tuesday, Thursday after class, so you can try and coax the answers out of him today if you want. Any logistical questions, organizational stuff? Yes?
The homework is due on
Thursday.
So we'll get the upload pretty soon.
That's right. Yeah. So you have to upload a PDF. Oh. Oh, I'm sorry. Canvas.
Yeah, that's how I set up the assignment.
Fantastic. Okay. Yeah, upload a PDF on Canvas. Upload a PDF wherever it asks you for a PDF.
That's good.
Yeah. Yeah, and I forget what time of day it's marked. 11:59. Chris did that evil thing where now you guys are going to feel like you have to stay up all night. I usually make my homework due at 8 so that the students don't look ragged the next day. But you guys have till midnight, so enjoy. Any other questions, concerns, comments? There was one small bug on the homework that was actually typo, and then a few things that I reworded to be slightly clearer. So if you downloaded it before I posted on Piazza a couple of days ago that there was a typo, you should refresh. Basically, there's just a missing factor of 1 over n in front of one of the formulas. Many thanks to the anonymous Piazza poster for catching that one. Hopefully it's right now. I think it's right. We did it in my office hours, and Chris did it, and all of us agreed on the answer. In my original solution, I parenthesized wrong, because we're all human, and these things happen sometimes. Okay, fantastic. So with that, today our goal is to continue talking about linear system of equations, which is unsurprising, because that's basically what we'll be doing in this class for several weeks, which I know is exciting, and exactly why you all come to 6S95 whatever. Let's see. So we'll start with a little bit of review from our previous lecture. Make sure you're all caught up to speed on what we've been doing so far. And then our goal today is to do at least one thing, hopefully 2, and possibly 3. So we're going to start by showing that this Gaussian elimination algorithm that we wrote down in our last lecture can be kind of codified in a very elegant way that leads to a factorization of a matrix called LU factorization. So that's thing 1. Thing 2 is that then, now that we have linear solvers, we're going to go back and kind of talk about what are some computer science style applications of linear systems of equations, which sounds silly, but at the end of the day, so far we haven't actually motivated this problem, right? We've come up with solvers, but we haven't actually shown in what computational context they come up. Now that we are ourselves that linear systems are things that we can solve in fairly efficient time. Anybody remember what's the runtime of Gaussian elimination? n cubed, that's right, good work. Now we can go back and see that this enables a plethora of exciting computational applications that basically boil down to like backslash in MATLAB. I mean, there's a reason why in MATLAB it's literally one character to solve a linear system, which is that this is a really important little tool that in numerical software. Even if you don't like MATLAB, it's still true. Okay, so we'll do that, but then what we're going to do is look back at those applications that will motivate. We'll say, okay, all of these can be solved with the linear solvers that we've already derived, but we'll see that the matrices that are involved in those linear systems are kind of specialized and structured in a nice way, and that if we know a little more about our linear systems, we might be able to devise algorithms that are more efficient or more numerically stable. And in particular, that's going to justify or motivate the second matrix factorization we'll see in this course, which is something called Cholesky factorization, which is kind of a special case of LU for a particular class of matrices. Okay? I'm not sure we'll get to that today, but defensively, I worked it out on my notes to make sure that I get that calculation right should we get that far. Okay, so as a bit of review from our previous lecture, remember our basic goal in these lectures is to solve this very complicated looking thing, which is ax equals b. Here we are assuming that a is in Rn by n, so it's square, and b is obviously in Rn here. And we talked at the very beginning of the previous lecture why we want to make that assumption, right? Because otherwise, it's not even clear that this problem is well posed. Right? Remember, when I use that phrase well posed, this is very common numerical analysis lingo. It means like solvable. Yeah? Okay. So in particular, the algorithm we wrote down, which I'm guessing many of you have actually done by hand since high school in some fashion or another. You might not have called it this, and you might have thought of it more as problem solving, less as a boring algorithm. But like one way or the other, you're basically doing one of three things in the process of solving your linear system, right? You're like permuting the list of equations, which is like permuting the rows of a matrix. You're doing forward and back substitution, right? Which is like taking a row of a matrix, scaling it, and then adding it to another row. And then you're doing a third thing, which I forgot. Oh, you're scaling the rows of your matrix just by constants. Yeah? And that those things alone can take a system, like for example, this augmented matrix like we talked about last time. And then after you do this row reduction process, you end up with identity on the left-hand side, and then the solution to your linear system on the right? And that was sort of where we left off. The algorithm looks something like what's on the screen here, where what you do is, right, you start with this sort of generic matrix. Remember, we kind of did it in this very schematic way, where like we don't know what these elements are, we just know their numbers. And then our goal is to eventually get kind of an identity matrix here, right? So we did things like scale the first row by 1 over this element, so that we know that there's like a 1 here, and then did like forward substitution to put zeros here. And those processes are summarized on the slide here, right? Now, the algorithm as is written on the slide here has this sort of, what was I going to say? Oh, it's missing a potentially optional piece, which is what we call pivoting. Right? Remember that pivoting is where we like swap the rows or the columns of our matrix to make sure that this very first step where we scale a row to get a 1 is well posed, right? We don't want to divide by 0. Yeah? So the canonical example you should remember when you think about pivoting is a very simple matrix. It is 0, 1, 1, 0. What's the inverse of this matrix? It's the same thing, yeah. If you square this thing, you get the identity, right? So does anybody know a fancy math term for what kind of matrix that makes this thing? This is just trivia at this point. It's like bar trivia. It's called idempotent, right? So you square, you get the identity. But in any event, that's completely irrelevant here. What does matter is that when I do pivoting, right? Yes. Idempotent. Hopefully that's right. You guys should Google that and make sure I didn't get it wrong. I'm definitely not ad-libbing this lecture. No, okay. But in any event, remember the first thing we do is scale the first row so that we get a 1 here. But what goes wrong here, there's obviously nothing I can do to scale this first row to get a 1. So the first thing I need to do is swap these 2 rows before I do that. Yeah? And so this is the sort of canonical example where you remember where like pivoting isn't just like a thing to make numerical stuff better. It can be, for example, like maybe I put some very small epsilon here, right? And then you might still want to pivot just to avoid dividing by a small number. But there's some cases where it's actually necessary. You have to do it in order to invert. On the other hand, one thing that you can convince yourself is that so long as A is invertible, if you do Gaussian elimination with some species of pivoting, it is guaranteed to solve your linear system. There's never a case where it doesn't. Okay, so right, and so in class we justified this algorithm, and then we kind of observed that we can think of each of our row operations here as kind of pre-multiplying our system by some elimination matrix E, right? That was either permutation, scaling, or this funny forward substitution, which remember took this little form like I plus a constant times E, I don't know, L, E, J transpose. I forget the letters we used, but matrices of this form, okay? Any questions about our story so far? Fantastic. Okay, so today our first order of business here is to address a use case which comes up all the freaking time, which is the following. So let's say that I have a whole sequence of linear systems I want to solve that are like AX equals B1, AX equals B2, AX equals B3, and all of these systems, the A is the same, but the B is changing. This is a very common situation. Like, for example, maybe I like set up a linear regression problem to, I don't know, predict the value of the stock market given like the last 10 days, right? And so I have this like sliding window, and so the linear system is always the same, but like the data on the right-hand side is changing. There are many different settings where that comes up, okay? In fact, in homework 2, you will implement such a setting. And my gentle hint for that homework, even though you haven't started it yet, is that you're going to need to prefactor your matrix. Okay, but in any event, here's the thing. So again, Gaussian elimination, as our colleague already mentioned here, takes cubic time, right? So eventually, like if I have on the order of n of these systems, it's going to be like quartic time to solve all this stuff, right? Because I just start Gaussian elimination over and over again. And the question is whether we can do better, right? Like, can we do something to just analyze A, because that's in common in all of these things, and then kind of maybe remember it in order to make Gaussian elimination more efficient when we're presented with this sequence of B's, right? And that's really, I think oftentimes when we do numerical linear algebra, we jump right to the punchline, which is this thing I'm calling LU factorization. But I think that's really the right way to think about LU, is it's just remembering the steps of Gaussian elimination. That's really all it is. And in order to kind of deepen our strategy so far, here's the observation that I think is really critical, which is that we made a lot of decisions during Gaussian elimination, like how to pivot, right? Like we had to scale rows by 1 over constant to get a 1 in the corner. We had to swap things to make sure that like there wasn't a bad number here. Did any of these, like in this augmented system, if you look back at those steps, none of them depended on B. They only ever depended on the entries of A, right? We never get more than the first n by n block of this thing. If you look at this algorithm, that's certainly the case, right? So that's like a good hint that somehow we're repeating a lot of work, right? If we do AX equals B1 and then AX equals B2, in both of those, in the algorithm we've laid out, we're likely to choose the same pivots, we're going to scale by the same values, we're going to do the same forward substitutions. The only thing that changes is that very last column, right? And so somehow that's something that we'd like to codify. Does that make sense? Now, moreover, so far we've talked about, I keep repeating n cubes, and because I want to get you in the head that like, once we have this LU object, what we're going to see is we can solve it faster, namely n squared. And in particular, there's going to be a motivation for why that's true, and that's the following. So let's say that we got halfway through Gaussian elimination, so now our augmented matrix looks something like the right-hand side. Hopefully, do you guys all kind of understand this like goofy schematic that I keep drawing? Like essentially the x here is a placeholder for like number that I don't know. Okay, so how long does it take? So I could consider this matrix over here on the left-hand side to be A and this thing to be B, right? This is like a very special structured linear system, right? So the matrix here only has entries above the diagonal. Does anybody know what the term for this is, by the way? I know our colleague knows the answer. Maybe somebody else? I know more than one of you do. Upper triangular, yeah, because it looks like a triangle. This is a very deep piece of terminology. So let's say I know that A is upper triangular, and I want to solve AX equals B. I claim that I can solve that linear system not in cubic time, but actually in quadratic time. Yeah? And here's the kind of sneaky thing. So let's say that I do back substitution here. So I want to take this 1, and I want to propagate it up to cancel the zeros. Okay, so how do we do back substitution? We kind of took multiples of this last row and then added them to the previous ones, right? But what are all the values to the left of the 1? Louder. With some gravitas. It's 0, yeah. Okay, so we're multiplying a bunch of numbers by 0. And then we're adding them to stuff above the zeros. Did I really have to do that? No, right? So in fact, notice that I can basically do at least this very last column in linear time because the only values I need to touch are the 3 x's above the 1. Right? Everything else I know when I back substitute isn't going to change. Does that make sense? Isn't that sneaky? So now I do one step of back substitution. And again, that's order n time. I have a matrix that looks like this. Look at what happened. What is the second to last row now? How many non-zero values does the second to last row have? 1. There's only 1, 1. Everything else is 0, guaranteed. So how long does it take for me to back substitute that 1? Yeah, two steps. Like it's again linear in the number of rows here, right? Does that make sense? So again, if I want to eliminate these 2 x's above the 1, right? The only number that I need to back substitute is this 1. I don't need to worry about things to the left or to the right. Okay, so I do that back substitution. Now I get 2 zeros, and notice that the same pattern keeps happening this way. That like very sneakily, when I do back substitution with a triangular system, I'm basically sticking a bunch of zeros in very convenient locations to make this whole thing take linear time. There's linear time per step. There's n steps total, so here it's quadratic time total. Does that make sense? This is fantastic. So this is, by the way, like Mazel Tov, everybody. This is our first example of a structured linear system of equations that I can solve faster than just generic ax equals b. And this is a very common theme in numerical analysis, that like, if I had Gaussian elimination, I can solve any invertible ax equals b problem. Like literally any. You hand me one, I'll solve it with Gaussian elimination. Is that necessarily the fastest algorithm? No. And so, or even the most numerically stable? No. Right? If I know a little more about my matrix, for example, I say, I want to solve ax equals b, and I know A is upper triangular, then I can do better, right? I can use this technique. Does that make sense? We're going to see so many examples of that in this class. So the first is triangular. The next will be a positive definite. Later we'll talk about sparse. All of these are structured matrices that can be solved faster than cubic time. Oh, I should be careful. Sorry, that was a lie. Positive definite will be also cubic time, but the constant will be shaved off. Okay. So don't message me on Piazza. I'm sorry. Okay, okay, we now have a lot of clues that we can do better, right? Because somehow we know that, like, for example, once we get past that first phase of Gaussian elimination, there's like something quadratic happening here, and the question is like whether we can kind of jump to that step or not. Does that make sense? So here's going to be kind of the way, and again, this is a very idiosyncratic, like this is Justin's way of thinking about LU factorization. You're in my class, so sorry, that's how it's going to go. So remember that we're thinking about these elimination matrices, and we've already argued that essentially we can think of all the steps of Gaussian elimination as just like pre-multiplying by some structured matrix. So we started with like ax equals b. I'm going to put a bunch of space here, like that. And then what do we do? Sorry, we like applied like E1, right? So maybe that was forward substitution, and then like maybe E2 was scaling eventually, and then we have like En. Actually, I should be careful with n. Let's call it m. Right? Yes?
Can we swap B with identity matrix? In that case,
Yeah, that would be a way to solve the linear system. Yeah, absolutely. Well, so far we don't get the inverse. So you're right. If I take this all the way to completion, I get the inverse. It's often unnecessary to compute the inverse of a matrix. But that is a thing that we could do, for sure. Incidentally, if you want an example where that would be ill-advised, think about the matrix like the linear system, something like that. So like generically, you don't really want to invert this matrix because of the epsilon, but this particular right-hand side is kind of okay because it doesn't really involve that epsilon. So that's the kind of case to think about for numerical stuff. But that's an aside. Let's say that I do, because we kind of know how to deal with upper triangular systems. right? That's our little clue as to how to get quadratic algorithms. Let's say that I just do the first phase, just the forward substitution part of Gaussian elimination. So by the time I finish that, what happens here? What is this product? What do we know about it? Remember our little schematic, like with the zeros, the ones, and the x's? If I just do the first phase, which again we call forward substitution, well, what we just argued is that this matrix is upper triangular. Yeah? Okay, so this thing is upper triangular. So let's give this matrix a name. U. Let's call it, I don't know, B. We're gonna we're gonna avoid U for a second here because we're gonna see that we might want to reserve U for a slightly different matrix. Okay. So in other words, yeah, we essentially argued that like E1 times A is equal to B, which is upper triangular. Okay. Now here's going to be the next kind of sneaky thing. We're going to think about Gaussian elimination without pivoting first, then we're going to come back to pivoting later. Is that okay for now? We're going to assume that we never have this weird boundary case where there's like a 0 at the leading entry, which it turns out happens with probability 0. Like you have to specially construct that matrix. Then what are these matrices? They're one of two things. They're either row scaling or they're forward substitution, like that. Oh, actually, I'm sorry. I'm going to call this matrix U. That one's fine. It's very hard to anticipate a calculation while you're doing it live. But this one can be, we can call this U. But what we have to be careful about is this guy, because we're going to invert it. But in any event, hopefully I haven't totally lost you guys by renaming a matrix U. Is that okay? Okay. So U for upper triangular. This notation, as our colleague suggests, makes a lot more sense. Okay. So row scaling matrices, what do they look like? This is not a trick question. Like, what kind of matrices are these things? Diagonal. Thank you. Okay. And remember, the forward substitution has a very particular form. It's I plus C times E, L, E, J transpose. And it's forward substitution. So what do we know about the relationship between these two indices? You have like a 50-50 shot here. But if you think about it, L has got to be bigger than J, right? Because we take row J, and then we copy it to row L, which is below it, to cancel it out. Does that make sense? Yes? No? It's some kind of acknowledgement? Like, look up, like, yes, Justin, I'm so excited about what's about to happen to this matrix. Please? Oh my God. Okay, so that's right. So what does this matrix look like? Well, I've got the identity, like that. And then this matrix is like ELEJ transpose is a matrix with a single one in entry L comma J, which now we know lives below the main diagonal. Okay, so it's like a 1 like down here somewhere. Yeah? So in particular, what kind of matrix is this thing? It's a lower triangular matrix. Oh my God. Right? This is so exciting. So now, like, the plot thickens. Do you see that? We have a lower triangular matrix times A, right, is equal to an upper triangular matrix. So now we're like so close to being structured. Everybody with me so far? Okay. This is the one, by the way, this is where I wanted to be the tiniest bit careful. We're going to call this thing L inverse. Right? So in other words, we've shown that there's a lower triangular matrix A inverted, which equals an upper one. That's really what we've justified so far. And now you can see why, is that we can move this to the other side. We have LU. Now the only thing we have not justified yet is that the inverse of the inverse here is also lower triangular, right? That's what we're missing. Everybody with me so far? Is this exciting? So notice, by the way, if we're going to jump to the the punchline here. Let's say that I want to solve ax equals b, and moreover, I know a equals LU, right? Then it's quadratic now. Why is that? Well, we know that x is equal to a inverse b, right? Remember, what is the inverse of a product? Time for some linear algebra review, everybody? Maybe somebody new? What is the inverse of LU? Yeah, not somebody different, but that's okay. U inverse L inverse B. So if I kind of parenthesize it like that, right, I can write an algorithm for solving ax equals b by solving this triangular system first. And then maybe we give that a new right-hand side. We'll call it y. Now we solve a new triangular system with u. Does that make sense? Nod? Acknowledgement? Yeah, cool. So this is exciting, but I still haven't justified that we actually have the L and not just L inverse is lower triangular, right? That's what we're missing. Okay, right, so let's catch up on our slides a little bit with the story. I got so excited that I gave away half the story here, I'm sorry. But in any event, now we see we get this upper triangle. I'm sorry, I called this M and these E, my bad. But whatever, we applied a bunch of elimination matrices just for the first half of Gaussian elimination. That uncovered an upper triangular matrix U. And now we know that we can write A in this other form. Right, so here I've chosen to eliminate or to invert each of the m's one by one. And yeah, we're going to call that this product here L. Does that make sense? So what's left to prove? Well, what's left to prove is that this thing is actually lower triangular. Right? We haven't actually shown that. We've shown that the inverse of this thing is lower triangular. We haven't shown that this product is lower triangular. Okay? And so there's a lot of different ways to do that. Conveniently, L, we have a factorization of it. We know that L is the product of all these m's, right? And so if I can work out the inverse of each of these m's, then I could compute L directly rather than L inverse. Right? I could multiply all those together. And that's what we're going to do. And so we're going to do two things. We're going to show that each of these inverses is by themselves a lower triangular matrix. And then we're going to show that the product of two lower triangular matrices is itself lower triangular. Does that story make sense? I'm talking really fast because I get really excited about LU factorization. This is a big deal to me. Okay, yes?
You might have said this and I missed it. Why is it called LU factorization?
Oh, because I wrote A as the product of L times U.
It's just because the variable names that you're
Yeah. but no, yeah, L stands for lower and U stands for upper, right?
Okay, I get, yeah.
So yeah. This is a kind of funny thing in this community. The next matrix factorization we're going to do is QR.
Yeah.
And that's because the first person that derived this thing called them Q and R.
Fair, okay. I can argue that.
Yeah, but I think, yeah, and the frustrating thing is they could have called it QU, and that would have made sense, because U is R is going to be upper triangular, but they didn't, and now we all, yeah. Okay, so, everybody with my story so far? Good. Okay. So, what do we need? We need to be able to invert all of our different elimination matrices. And notice, by the way, so far, the conceit of this little derivation here was that we didn't need pivoting, right? We're going to come back to that. I'm going to keep repeating that because that's actually a really important message, that actually a matrix that requires pivoting does not have an LU factorization. Yeah. So like if somebody asks you, does every matrix out there in the universe have an LU factorization? Your answer should be no. It does have a PLU factorization where you permute stuff, but that's a little different. So just as a hint on your homework, if you find yourself using the LU factorization and there's a problem on your homework that says your algorithm needs to work for all matrices, then you might want to reconsider whether your answer is correct. Okay. So the question that we need to answer is, why is this L thing triangular, right? We know that L is the product of a bunch of matrices that are all inverses of matrices of the form I've put on the screen here. And so we're going to do this in two steps. We're going to show that the inverses of these two things are lower triangular, and the product of lower triangular stuff is itself lower triangular. I feel like I'm like saying lots of math words really fast. I feel very technical right now. So first of all, the inverse of a diagonal thing, right? So like S inverse here, this is the inverse of a diagonal. Anybody want to give me, just for yucks, like what is the inverse of S? I think we can. Yeah, it's another diagonal. In particular, just for completeness and for problem solving. That's right. So this is just 1 over A1 to 1 over A n. So far we're cooking with gas. Okay. So the other thing we have is this this pesky bugger. So this is E L E K transpose, right? Where here we know that L is bigger than K. So inverting this matrix, I think, is annoying symbolically, like thinking about how to invert such a thing. But let's think about it kind of like spiritually for a second. So what is this matrix doing? It's taking row K, scaling it by C, and adding it to row L. What would I do if I wanted to undo that operation? Well, I'd take row K, scale it by C, and subtract it from row L. Yeah? So I'm going to write that in symbols. What is E inverse? Yeah, it's just I minus C E L E K transpose. That's it. And obviously this thing is lower triangular, right? We just flipped the sign of the lower triangular piece. Okay, so now we all agree L is a lower triangular matrix. So the only piece that we're missing is this little proposition we've written on the board. Okay. This classroom is annoying because I only have 2 boards to write on. Is it okay if I erase this little amount of writing here? I could, but then this camera it's a whole situation here. Okay. So we need to show that the product of, do I want to do upper triangular or lower? For some reason in my notes I did upper. Are we brave enough to swap from what's on my lecture notes? That's a good way to make a mistake in class. Sure. Is, I don't know, lower triangular. Okay? All right, so what's going to be our proof of it? So let's say, I don't know, take A, B to be lower triangular, right? So what does that mean? That means that like Aij equals Bij equals 0 for all J, if I go bigger than I. I don't like doing proofs that I didn't write in my notes, so I'm very nervous right now. Okay, this is an emotional moment for me, and we're going to work together. Okay, so we're going to define C is equal to A times B. Okay? This is one of these proofs. This is like the sort of like Toucan Sam approach to mathematics, right? We're just going to kind of follow our notes, like write the formula, and then just start expanding stuff, and like the result will just pop right out. Okay? So we want to show, obviously, that C is also lower triangular. So suppose J is bigger than I. We want to show that Cij is equal to 0, right? So what we can do is just write a formula. Yeah? So what is Cij? Well, remember how matrix multiply works. So it's like this. Or really, I should face this way when I do it. It's like that, yeah? So Cij is equal to the sum over maybe K of Aik Bk J. Hopefully we all agree. Good so far? Okay. So what are we gonna do here? How do we split up this sum? Well, so let's kind of draw this schematically. So we have A. This is A. We have B, like that. And we're doing one of these products. Then notice what's going to happen. Like if I move across a row here and a column there, from here, hopefully this picture is becoming clear what's going to happen, right? So we've got a bunch of zeros there and a bunch of zeros there. All right. Okay. So what can we? How can we split this thing up? Well, we can say, okay, so this is really A I1 B 1J plus A. So what's going to happen? Maybe we do IJ B J. Sorry, I'm like reverse engineering the proof of this flipped backward formula. Like that, plus A, I, N, B, and J. Right? So all I did was just take this sum and expand it. That makes sense? Okay. Remember that J is bigger than I. And moreover, these things are equal to 0 anytime the second index is bigger than the first. Yeah? Okay. So let's look here. So first of all, the second index is bigger than the first there. Right? So this is 0, like that. And in fact, if we do plus dot, 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 maybe I insert right here plus A, I, J minus 1, B, J minus 1, J, plus all this stuff, right? So this is just the previous term in the sum, right? All of these have the same B equals 0, right? Because B is lower triangular. That kind of corresponds to this part of the product. Does that make sense? I think this is one of these proofs that's more annoying to write down than to draw schematically. Okay, and then finally, for the remaining terms, now we start here. Well, remember that J is bigger than I. So A is lower triangular, so now these terms are 0, all the way to the end. Does that make sense? So essentially, I took my sum and I split it into two halves. The first half is 0 because of the B's. The second half is 0 because of the A's. Does that make sense? So what did we show? We showed this whole thing is equal to 0, and hence, C is lower triangular. That's what the check mark stands for. Okay? That was my freshman intro to proof professor back in the day, who is a person in my research community who I will remain nameless. Used to take off points if you did check marks at the end of your proofs. So I don't like victory marks. You're supposed to do that, right? I think check marks are perfectly fine. Okay, so we have justified the proposition on the screen, and hence we have shown that every matrix that we can do forward substitution and back substitution on that does not require pivoting, we can now factor as LU. Any questions? Okay, this is exciting. You guys don't look nearly excited enough. You just learned something about the universe. You can write any square grid of numbers almost and factor it in this beautiful way. That's super cool. We didn't know that before. Right, and again, if we want to solve Ax equals B, we can do it in 2 steps, and both of these take quadratic time. Okay, so some other fun facts. How much memory should it take for me to store my LU factorization? In this case, we're gonna, instead of just thinking about big O, let's think about actually like counting. So, n squared. Why is that? Mm-hmm. That's absolutely right. Yeah. So again, to repeat what our colleague has said here, so far we've shown that we can factorize as LU. The additional fact we need is that we can take one of those two guys and make the diagonal equal to 1, and so we don't really have to store it. And I'll let you think about why, for any invertible matrix, that's okay. That's right. So on the screen, here's what I mean. You could maybe store U in the sort of upper half of a matrix and L on the bottom. Now, as a warning, does it make any sense to take a matrix vector product with this matrix? No, this is just a memory compression technique. So be very careful in your code should you decide to use this thing. Okay, so again, really, when you're computing LU factorization, the actual algorithm, if you look in the textbook for the pseudocode, I don't think it's worth deriving in lecture because it's one of these kind of finicky things that you'll all believe and happily agree with, and then go home and still struggle to derive the pseudocode because it's just annoying to think about. It's just going through the steps of Gaussian elimination and just remembering them in a matrix. That's literally all it's doing. Okay, that makes sense? Everybody with me so far? Yes, yeah, that's absolutely right. That's a fantastic question. So LU factorization takes n cubed time. Once I have that factorization, it takes n squared time to solve a linear system. So there's some times when it's not so valuable to compute it, and sometimes when it is. That said, I think even if you solve like 3 problems, the constant factor is such that it's still beneficial. Moreover, they're extremely fast LU factorizations for sparse matrices, where what you do is you try to like avoid introducing non-zeros in L and U. This is kind of a sneaky trick. And in that case, it can be even faster than cubic, but that's a little outside of the scope of this class. Yeah. Okay, so one more review question. You might notice that this is a thing that I care about. Does every matrix admit an LU factorization? I'm going to vote no. I'm going to vote yes. I'm going to vote like, hell no, I'm not raising my hand. Apparently the 2 guys in the second to last row. You know, like we're just not going to participate. Obviously your instructor is desperate for attention and we don't even care. That's fine. Okay. So remember our way out of this particular problem was to introduce something called pivoting. And there's actually 2 kinds of pivoting. Oh, there's sort of 3. One is like you swap the rows of your matrix. One is you swap the columns of your matrix. And one is you do both. Okay? So the easier one to derive a sort of LU-like factorization is actually column pivoting in my mind. And here's why. So let's say that so far we've done row operations, right? We've like swapped rows of a matrix, right? Let's say I want to swap the columns of a matrix. Then essentially all I do is I post-multiply by the permutation matrix. Does that make sense? Like remember that row operations you kind of multiply on the left. So you can kind of think of like column operations as multiplying on the right. So if you go back through the steps of Gaussian elimination, you can convince yourself pretty easily that you could get a form as the following. So every time I eliminate, I multiply on the left. And every time I permute the columns, I multiply on the right. And when I go through all these steps together, I can get an upper triangular matrix. Does everybody kind of see where this expression is coming from on the screen? And so what does that mean? Well, okay, the left guys are all still lower triangular. I've got U here, so I have this LU, but now I have the inverse of a permutation matrix that I need to take care of to isolate A, and that's what's bringing this P factor on the right. So, does every matrix admit an LU P factorization? Which is actually yes. Yeah. At that point, you're good. Yeah. Yep, that's a fantastic policy. So for those who didn't hear, the question was like, how do I choose a pivot? And remember that like numerically, the most stable thing to do is usually to divide by a big number. So a very common sort of heuristic is to find the largest, in this case, value in a row, right? Because you're swapping the columns, and then pivot to put that in the position you're about to divide. That's not the only one, but you know, then there's a policy called full pivoting, where you can swap rows and columns, and in that case, you can find literally the biggest element in your whole matrix and maybe put it there. Yeah. Oh, that's a fantastic question. Thank you. So let's say I want to solve a linear system, but now I have this LUP factorization, right? So I want to solve, let's see if I can do it in this space here. You know, so apparently when my mom went through like teaching school, they actually had education on board management. Obviously, I have not had that. Okay, so let's say I want to solve AX equals B. Now I factor A, so I have LUPX equals B, right? So then X is equal to P inverse U inverse L inverse B, like that. And so far, we kind of know how to solve this piece, right? These are triangular systems, so we know how to solve it. Does anybody remember what is the inverse of a permutation matrix? Not quite. So think about a permutation that takes like a list from 1 to n and just shifts everything forward, right? So clearly, if I do that twice, I have it inverted. Transpose, that's right. The inverse of P is just P transpose. Or similarly to the question, that really does mean just like kind of permute it back. Those are equivalent things. Yeah. I mean, because if you think about it, remember the non-zero entries of a permutation are like I comma sigma of I, right? So if I take the transpose, they're kind of like flipping the role of those two indices. Yeah. So this step really takes linear time. If you store P as a permutation, not as a giant matrix. And then these are quadratic, so you're still good. Fantastic question. Any others? Mm-hmm. Yeah, you're right. Like if there's a big range of values in your matrix, then you're going to start leaving the range of the numerical precision. I think there are probably some really fancy ones out there where maybe you choose a value in the middle that tries to not have anything overflow. But I think almost all of the implementations I know of just choose the largest, because that's the one that causes the most precision issues, is when you divide by a small number. But you're right. You could imagine cooking up all kinds of weird heuristics here. Or maybe you want to save computational time by not iterating over the whole row. So maybe you like randomly draw one, because with high probability you don't get the messy value. I mean, you can even think of like all kinds of weird stuff. Yeah. You actually do. We haven't justified it here, but yeah. That's a great question. You do have if you're not invertible, you're still good in this setting. You'll have to think through why like the forward the substitution steps are kind of okay. Yeah. Mm-hmm.
So you said last time that we don't want to enter A.
Mm-hmm.
Why?
We never store A inverse. We only ever store L and U. Those matrices, it turns out, are much better structured. That like they're not sort of the composition of a million operations we apply to A. It's far fewer than that, right? Like the forward substitution thing is really just like 1 over a value in the matrix, or like some very small piece. Well, it turns out this is generically a slightly more numerically stable thing to do. The real justification is more just for many right-hand sides. And ill-conditioned matrices are ill-conditioned no matter what solver you use. But I do, at least the mythology is usually that LU is slightly more stable. You're right, though, that like at the end of the day, you're just simulating Gaussian elimination. So like, it's not so bad. The one saving that you do have is when you store A inverse explicitly, there's the rounding that it took to store A inverse, which is slightly less than the rounding that takes place in storing L and U separately, right? So in that case, you're sort of, instead of like storing 1 over some values in a matrix, you're sort of storing the values and then doing division on the right-hand side instead. But you're right, that's a little bit more finicky to think about. These are fantastic questions. I'm glad you guys are thinking critically. Okay. The other thing you might ask is can you do the other way, like PLU? The answer is yes. There's a little homework problem in the textbook. I decided not to assign it to you guys because it's a little annoying for how to do that. But if you want to think about like why that's slightly more annoying, if I do Gaussian elimination with row pivoting, then I'm going to pre-multiply by permutation matrices. So I don't like conveniently get all the permutations grouped on the right-hand side. They're now kind of interleaved with the e's. And so you have to kind of justify that you can like commute a permutation matrix in one of the e's that we have here and still have a nice expression. Right? So that's where things are a little annoying. Yeah. So this concludes our discussion of LU factorization. Any final thoughts, concerns, questions, comments? No. Well, good. I'm glad that you guys are thinking carefully. That's just fantastic. That makes me very, very warm and fuzzy inside. Okay. So now the next part of our course here, now that I've kind of justified that like linear systems are things we can solve in polynomial time for sure, and really pretty efficiently. I mean, like as n-cubed algorithms go, like this is one that's really just like 3 for loops on top of each other. It's pretty simple. You know, in some sense, we're going to do what I consider to be not necessarily the best version of math, where we've like invented a hammer and now we're going to go out and look for some nails. I think usually it's better to teach the other way around. But I think in this particular case, since you've all taken linear algebra, maybe this is okay. But now I'd like to go back into computational world and kind of think through what are some of the applications of LU factorization and solving linear systems. And we're going to examine the matrix A and come to the conclusion that oftentimes our matrices A are actually really nicely structured. And we're going to use that to derive even better factorization. Does that make sense? Okay. So, I mean, the basic point here is that like linear systems are like stupidly important. Like if there's one thing you get out of this course, is like solvers for linear systems exist. They're things I should use in my code. The rest of this is secondary. And so anything you can do to take your favorite messy numerical problem and get it pretty close to solving AX equals B is a good thing. And so we'll see a few examples of that. Many of these are probably review for some of you, and that's okay, because really our point here is to look at the matrix. It's less to think about the details of the problem. Okay, so our first example, which is always everybody's first example, is something called linear regression. This is also the first example where something will go wrong with our solver. So let's say that there's some function f of x, which we'll say we write in this very complicated form. If you want, we can call this a zero-layer neural network. Does that wake people up a little? And so I'm given a bunch of pairs like x comma f of x, right? Like I have, for example, maybe I'm trying to like predict the height of a plant after I apply so much water and so much fertilizer, right? So the x would be the water and the fertilizer, then the f of x would be like the height, you know, and maybe I have some model that says that one is linear in the other. Obviously that would be a bad model, but it's a very simple one. So my task here is given a bunch of x f of x pairs, I want to kind of solve for the a's, right? So to write it in an even messier fashion, if I have these x upper k, so upper k here is indexing what data point I'm in, right? Then I have a bunch of these xy pairs, and now I'm trying to recover the parameters of my model. Okay? So what is known and what is unknown? Like what is the input? The inputs are the x's and the y's, and the output are the a's. I think it's easy because we all want to think ax equals b. This is one where actually that's not the case. So what do we notice? Each of these expressions involves the same set of unknown values a, and they're just combining it with different weights, the x1 through xn here. Yeah? So really, you can think of this as like the dot product between a and x superscript 1 is equal to the first guy. The dot product between a and x superscript 2 is the second one. The reason why we're going through this, by the way, is mostly to get you thinking about structured matrices and linear algebra. And in particular, we can write this in a much cleaner fashion, which is as follows. Maybe for now, we trust our data completely. There's an equal sign. We're going to come back to that in a minute. Does everybody agree that this set of expressions on the previous slide is actually equivalent to what I've written here? So in case this is hard to think about or you're not used to it, that's perfectly fine. Remember that, again, you always have to do the same little dance for matrix vector multiply, like that, right? And if I want to take a dot product between two vectors, I could like take one vector, flip it on its side, and then multiply it like that. That's precisely what's going on here, right? So I have x1, dot product with the a's gives me y1, x2, dot product with the a's gives me y2, and so on. So for example, on your homework, I give you a matrix whose columns are just a bunch of data points. And this is why, like the very first part of your homework problem in the coding thing is to derive the kind of matrix version of an indexed expression, which, by the way, I think is like roughly what our machine learning graduate students spend about 82% of their time doing. Chris agrees. He doesn't know if he agrees, but he does. Okay, so more generically, maybe I have some set of functions f1 through fm. And I put the weights on the outside, then I can still do such a thing and factor the s, because conveniently here, the linear part is in a, it's not in the x's, right? So for instance, let's say that I want to fit a polynomial to a bunch of data, right? So it would be like, in fact, so on the next slide here, a0 plus a1x plus a2x squared and so on. This is a nonlinear regression problem in the sense that f is nonlinear, but remember our unknown isn't x's, it's the a's. So that actually is a linear problem. Does that make sense? Incidentally, just for fun, the matrix of this linear system for this first problem here. Oh, man. You know what's really not fun is building a career in numerical analysis and having a chalk allergy. This was a bad decision on my part, and I regret it every Tuesday and Thursday. Okay, so right, so what does this linear system look like for regression? So again, we have a naught, a1, an, right, because those are our unknowns. And then like, so maybe I have, y1, yn, like before. What does this matrix look like? So what is the first element? So remember, it's a naught plus like x1 times a1 plus x1 squared times a2, and so on. Right? So at the end of the day, it's going to look like 1 x1 squared to x1 to the n, and so on. So if we go in this direction, this is the index that's going to change. Does that make sense? So notice this matrix has a really weird form. Do you see that? Like all of the elements here are just different powers of the same number as you move across the rows. This is a very special matrix. It's called a Vandermonde matrix. This is a nice example of a very structured matrix, but one that's actually not necessarily very easy to invert. Yeah, just fun fact. We're not going to go into like specialized algorithms for polynomial regression because I think that's kind of niche. but this is just an interesting example of a weird matrix. You can also kind of understand Fourier transforms in a very similar fashion. Notice, by the way, like if I wanted to fit a function of the form, x plus phi inside of cosine, we can use our favorite like angle sum identities to kind of isolate the phi and the x, and what we'll end up with is still a linear problem in the end. Okay. So obviously now we have a powerful thing. We can solve machine learning problems. If you want to call it machine learning, which these days I think we do, right? Like if we have a linear form for f and a bunch of data points, we can now solve our linear system and recover the a's, and now we can predict the value for other x's. Yeah? Here's the problem. So if I want to do polynomial regression, like let's say I want to do cubic regression. First of all, I'll ask the same question I always ask my graphics students. If I want to fit a cubic to my data, how big is my matrix here? How many columns? 4. Good, you didn't fall for my trap. You gotta remember the 1 here. Right? It's 1x squared, x cubed. 4. Okay. But is there any reason why, like if I want to fit a cubic function to data, I should have exactly 4 data points, right? Like we only know how to solve square matrices. I'm being a little facetious. I think most of you guys know where we're going with this. The answer is obviously no, right? Like the shape of your model here, like the fact that you chose n equal 4, or 3 in this case, really has no bearing on the amount of data you might have. And of course we know this, that like, we shouldn't have to do exactly n experiments. And moreover, so far we have an exact equal sign in our linear system, which is fishy because data is noisy, right? In fact, by the way, specifically in polynomial regression, we'll come back to this later in this course when we talk about interpolation. There's something called RUNGE phenomenon, which you should Google, which is really interesting examples where you fit polynomial to like data which like looks innocent enough, and for whatever reason, like the polynomial that goes through it is like some wild and crazy wiggly thing. So like it turns out you don't want to like, if I have 1,000 data points, fit 1,000-degree polynomial. Like this is a bad idea, even if your data points are pretty reliable. Okay. There's another term machine learning people or statistics people use for this, by the way. Overfitting, that's right, yeah. So again, what we've done so far is overfit, right? We set up a linear system that fits our data. So the reality is, we can kind of think of linear systems as kind of like observing dot products. Do you guys see how what we've done so far is yet another way to interpret ax equals b? That like every row is kind of saying like the dot product between the first row of a and x is equal to b1. The dot product of the second row with x is equal to b2, and so on, right? Right, Justin, this is an insightful thing to think about. Okay, so in some sense, we're like playing this funny game. Like we have a vector, and I don't know that vector, but I do know its dot product with a bunch of other vectors, right? And now I'm trying, like, can I recover the vector from all these dot products? This is just another way of thinking about ax equals b. Does everybody get what I'm saying? You look like you're about to fall asleep. You're killing me. I think it's these windows. We got to open these things. And it's a little hot in here. So obviously, somehow, if we have even more information, we should be able to do better, right? Like if we just keep adding rows to this this fun game where we measure a dot product, that's more information, and so we should be able to incorporate that in our linear system somehow. So in other words, what we'd like is maybe if we have more than n rows, is like some kind of approximate relationship like that. So what are we to do? I know you all know the answer. You know where I'm going with this. It rhymes with meest squares. Yeah, we're going to write down an optimization problem, which is this, right? So we no longer can find an x so that ax equals b, right? Because we know, remember our previous lecture, that for any tall matrix, there's very likely a right-hand side that we can't solve exactly. But we can try and get close, right? So one thing we could do is rather than solving system equation, we're going to now move to a variational language, or optimization language. This is find me the x so that this norm is as small as possible. Does that make sense? By the way, in this course, this release your homework, when we take norms, we're always going to put subscripts to tell you which kind of norm. So when there's the 2 here, this is like the square root of the sum of the squares. This is the thing that we're used to. On the homework, your norm is actually the infinity norm. It's like the max of the absolute values. Okay. So that's great. The only problem is that we don't have an algorithm for solving this optimization problem. So we need to do that real quick. So in particular, what we're going to show, of course, is that actually, here's this fun top secret fact, that this thing still can be solved with linear algebra. Yeah? Okay, so what I want is to solve this optimization problem, or the 2 norm. For convenience, hopefully we all agree that we can square. Okay? All right. And just for, well, I don't know. You can put a half there and it'll make the expression a little nicer, but like, yeah, this is fine too. Okay, so first of all, what is this expression? So ax minus b, take the 2 norm and we square it. In general, like whenever you see the 2 norm squared of a vector and you don't know what to do on your in life, you should remember that, of course, the 2 norm is nothing more than the dot product of a vector in itself. Yeah. So in particular, this is equal to ax minus b transpose times ax minus b, like that. This is Justin's favorite way to write a dot product, which is to transpose to a row vector and then multiply. Okay. I'm sorry, I didn't quite catch that. With matrix norms, then you can't do that. Then you need a slightly different thing. So the object you're talking about is Frobenius norm, and the equivalent identity, in case you're curious, is the trace of A transpose A. But that's out of the scope of our discussion for now. Oh, the spectral norm of a matrix. Yeah, we're not there yet. That's actually irrelevant because we're doing vector norms. So we'll stick with that for now. Okay. So let's simplify our expression here. So we're going to move the transpose inside. Remember what happens with transpose of a product? They swap the other way. So this is equal to x transpose A transpose minus B transpose AX minus B. So my favorite part of this job is expanding the square 1,000 times. Okay, so now let's do this whole thing out. You get x transpose A x minus, I'm not going to skip a step, x transpose A transpose B minus B transpose A transpose, no, wait, B transpose A x. Yeah, okay. Plus B transpose B. Okay. So I've done this only 5 billion times in my life, and I still manage to get things wrong. Okay. Notice, by the way, if we parenthesize like that, do you guys see that these two expressions are equal? They're both the dot product between x and A transpose B? Yeah? Okay. Cool. So we can write this slightly different way, just for convenience. X transpose A x minus, which way do I want to write it? X transpose A transpose B now times 2 plus mod B squared. Notice that this is just the norm of B squared. Okay. Whew. Everybody with me so far? Okay. So this is a function, by the way. We'll call it maybe f of x. So if we want to minimize it, what should we do? Yeah, take the gradient and set it equal to 0. Yeah? Okay. So what is the gradient? Well, hopefully you guys all did the assigned reading for this course. And so you know that the gradient of this kind of expression in x, we can just read off very quickly, is 2A transpose A x. If you didn't do that, might I suggest going back to the first chapter of the book a little bit? It's also like totally unsurprising, right? Because this is like a quadratic expression in x. Okay, and then this is the dot product between x and a vector. So of course this is minus 2A transpose B. Okay. If that went a little quick, you should go home and do a little calculus review. You don't need to leave the class, just do a little calculus review. That's all. Okay. So this thing is equal to 0 because we're trying to optimize. Yeah? So in other words, we have shown A transpose AX is equal to A transpose B. And here's a neat thing. This matrix is a square. So we can solve. Yeah, we have an algorithm for this. So secretly, this whole time, if we want to do least squares with a matrix that isn't square, we can do that. And the way that we do that is not by solving AX equals B, but rather by solving A transpose AX equals A transpose B. Does that make sense? Does anybody know the name of this extremely famous system of equations? The normal equations. That's right. You might ask why, and that actually is something I don't know the answer to. Okay, that's right. So these are called the normal equations. This is extremely famous linear system of equations. So life is good. Everybody with me so far? Fantastic. In fact, we can go a step farther. So maybe we take this problem, but we also don't want x rather, to be too wild. Like I know if there's some coefficient in front of one of these factors in my experiment that's like ginormous, something has gone wrong with x. So like, in other words, I want the norm of x maybe to be not so big, so maybe I add something like that, right? So in other words, I just penalize x from being too large. Right? This is a very common technique. In statistics, you call this ridge regression, Tikhonov regularization. There are a lot of different names for this. Or giving a Gaussian prior if you are in Bayesian statistics. All the same thing. OK, so in that case, if you kind of work through here, you'll end up with just A transpose A plus alpha times the identity, right? Because like essentially, all we've done is just added a quadratic term to this expression. Yeah? So even if we regularize our problem by the first thing, we're still good, and we can still solve with a linear system of equations. Isn't that cool? OK. Can we solve the other two problems, by the way? These are different ways to regularize that use other norms. Then can we use linear algebra? No. Yeah. Then we got to use stuff later on in this class. OK. So at least for this problem, we can do that. And really, again, I would say like 82% of a lot of like computational modeling research really just boils down to writing things in a funny least squares way and optimizing. Where like essentially you take a bunch of things that you have about some unknown quantity x that you all want them to be 0, and then you just square them all and sum them all up. If you're so lucky that all of the f's are linear, then you can use the techniques we're doing here. Otherwise, we'll talk later in this class about a very particular optimization algorithm called Gauss-Newton, which is exactly for problems of this form. Yeah? So as one example here, let's say that I want to align two images. Okay, so I take two photographs of this, I don't know what this is, church. And they're misaligned, like I'm walking around it a little bit, and I've applied a little bit of transformation. And in particular, maybe I mark points on both images. I say, like, you could imagine using computer vision software to do this, or you could imagine doing it by hand. So like I click the tip of this thing and the tip over here, and I label this x1 and that y1, and I do that for some set of points. Okay? Does everybody understand the input data here? So I have two misaligned photos, and then I have a bunch of points that are in correspondence between the two. Okay? So it turns out for small camera motions, a reasonable approximation is that the y's, like the positions in the second image, are basically a linear function of the positions in the first image. Does that make sense? So in that case, how would I model this kind of a problem? Any ideas? It doesn't necessarily have to rotate. In fact, I purposefully chose an annoying image where it's sheared a little bit. But you're right. Like generically, I could model A as some unknown matrix. Just say there's some ansatz here, which is I have an unknown A and an unknown B, so that I can take any x, multiply it by A at B, and get y. Right? So there's an unknown linear transformation that takes all my x's to y's. This is a model. In 3D, it doesn't work perfectly. But it turns out it works OK. For example, I actually coded this. Like this image really was generated this way. OK, so if I do that, just for fun, let's model this as a least squares problem. So what would I do? What are my optimization variables here? A and B, right? Notice I'm being sneaky in the class, and I'm trying to use like all the letters that are like somehow not intuitively variables to just make sure that you're thinking the right way. So like that, OK? And now maybe a very simple thing I could do is say, OK, well, I'm going to take each xk and transform it by my unknown transformation, then subtract yk. And obviously, this quantity should be 0 if A and B are good. Do you guys see that? So if I sum over my entire data set, this is a kind of a reasonable objective function, like a yardstick for measuring how good A and B are. Yeah? Okay. So I'd like to solve this optimization problem. This is actually a totally reasonable model, by the way. Like if you, like this is what a lot of these simple image alignment algorithms do. Yeah? Here's a skill that I want you to start kind of thinking about in practice. In the textbook, it goes through a lot of detail. But even if we just stopped now, notice that what is my expression? It's the sum of a bunch of stuff that's all squared and added together. So it kind of looks like a least squares problem. But there's an awkward thing here, which is that my unknown, in this case, is actually a matrix and a vector. Right? So somehow this feels like a different problem. Right? Like it doesn't feel like an AX equals B kind of. But the reality here is that it actually is, right? Because anytime the thing inside of the square is linear in your unknowns, and notice that it is, right? If I add together two A's, this expression just adds, yeah? Then secretly, this whole least squares problem is going to be a linear system of equation. In fact, if you work it out, what you're going to end up with is some matrix times A, 1, 1, 1, 2, A, 2, 1, A, 2, 2, B, 1, B, 2 times that equals that. So in the book, it actually works out these two matrices, I believe. I forget. I might have gotten too lazy to actually do it. But actually working it out from this might be like abstractly a little annoying because it feels like A is a matrix and somehow like I shouldn't be able to solve linear problems for matrices. But notice in order to do that, I had to kind of convert A into a column vector here. So that expression, sometimes if you look at numerical code, is called unrolling. So this is actually a problem where you can unroll it, and secretly it's the least squares linear problem. Okay. So anyway, I encourage you to take a look close into the book to kind of get more details there. But the basic point is that like least squares problems are in the wild all over the place. And like it's so easy in almost any computational domain to find such a thing. So let's do another example just for fun, which is the following. So do we have any computer graphics students here? Actually, I don't recognize any of you from grad students here. Oh, that's sad. One, fantastic. So this is a very common task in computer graphics, which is, let's say that I have a 3D triangulated surface, which is exactly what it sounds like. So I have a bunch of triangles in 3D that are linked together in a surface, like this face here. And I want to map it to the plane, right? So for example, in video games, this is a very common thing to do. I have like the 3D asset, like a character, and I want to paint onto the character a very high frequency texture. So I map the character into the plane, and I store the texture as like a JPEG, and then I map it back. And so there's a whole set of algorithms out there that are called parametrization algorithms, which is exactly what it sounds like, which is to take a 3D model and map it into the plane so that the texture can be stored as a flat image. Okay? There are so many algorithms and models out there for parametrization. This happens to be an area of my expertise, so if you like this kind of stuff, drop by office hours and I'll tell you way more than you ever wanted to know. But it turns out the most popular and simplistic algorithm out there uses nothing more than AX equals B to solve this problem, which is funny because this problem doesn't look like a linear system when I draw it like this. Yeah? So how are we to do that? So here's going to be our input data. It's going to be this 3D mesh, like the face that we have on the left-hand side. And for now, just for simplicity, we'll assume that it's a disk, like it's basically the image of a circle. So it has a boundary. And moreover, let's say that an artist has prescribed where the boundary should go. So like for all these points along the outer edge of this, ooh, I shouldn't have done that. For all the points along the outer edge of the face, I like map them maybe to the corners of a circle. And my job is to figure out where the interior parts of the face went. This is actually very common. I mean, it feels like a made-up problem, but it turns out that actually, oftentimes the artists want control over the shape of the boundary because they want to like pack it into a texture file in a very careful way or something like that. So there are a lot of different parametrizations out there, right? I could take the inside of that circle and warp it in some crazy way and end up with really tiny little squished triangles, or something like that. But here's a very common thing that we can do, which is as follows. So we can think of our triangle mesh as a graph which has a bunch of vertices and edges, right? So the vertices are like the positions of the points here, and the edges are the edges of the triangles, right? And a very common thing to do is to model these edges like springs, right? So I don't want any of the edges to look too long when I map it into the plane. Okay? So let's say that I have some variables here. Here are going to be my variables. It's going to be xi, which is going to be an R2, which is going to be the position of vertex I. Okay? So far so good? Okay. So our goal today is to model lots of least squares problems. And this is another one. So in particular, we're going to have a minimization over this set of all these different x-coordinates. And somehow, here's like kind of an interesting observation. Well, maybe we just want to put like a little spring on every single one of these edges here to kind of like try and contract them together, right? So like none of the edges want to get too long, and what's counteracting those springs from going to zero length is the fact that I've pinned the boundary down, right? So if I write an energy that measures that, what I would do is say, okay, so maybe for every edge ij, which is in my set E, right, I'm going to take xi minus xj, I'm just going to square it like that. Does that make sense? Does everybody see how this corresponds to, in some sense, good is a subjective term here, but like possibly a valuable parametrization, like one where, you know, if two x's are on the same triangle, they shouldn't be far apart in the image, right? That's what this is trying to do. Okay? And of course, what do we need? We need that xi is fixed for all I in the boundary. Right? Like, so in other words, remember, they pin down those vertices in the corner. Otherwise, the optimum would be to map the whole mesh to a point, because then all the springs are length 0. Yep? So this actually has a name. This, in fact, it has about 25 different names in different communities. This is an algorithm that goes back to the 1960s. It is called Tut parametrization. If you put weights in front of these things, then we give it a different name. Sometimes this is called harmonic parametrization. Anybody know why it's called a harmonic? If you're in the CCE program or you've encountered Laplace equation, this is secretly a differential equation model hiding here. That this is really an approximation of like the gradient of a map squared and integrated. But we'll come back to that later. Maybe in the very last lecture of this course, if we do differential equations, we'll come back to that, but maybe not. Okay, so here's the thing. This is a least squares problem. Now, there's a bit of a wrinkle here, which is that we have some constraints. Does anybody have any idea? Like, how could I essentially get rid of this constraint, because we don't know how to cope with that? We don't have, well, actually, there's multiple ways we could do this. I'll let you guys suggest. And then solve this using the linear solver that we've already kind of derived in this course. How should I do that? That's absolutely right. So here's a very simple thing that I could do, is I could say, okay, I'm going to take every term in this sum, and I'm going to say some terms involve fixed xi's, and some of them don't, right? And essentially, I'm just only going to have variables for the internal vertices, and for those ones, I'll just have some expressions where one of these two things is a constant. And now I have an unconstrained least squares problem, and we're back to things we know how to solve with linear algebra. Yeah? A different way to do this, by the way, is Lagrange multipliers. Also will give you linear system. Okay. So in any event, we're basically out of time today, so I'll let you guys take a look at the textbook that works through these things in detail. But essentially, the point that I want to make here is that all of these things are structured linear systems of equations. You guys see that? So for example, in the normal equations, we had A transpose A. And we'll see in our next lecture that this is a positive semi-definite matrix. Moreover, the matrix corresponding to this guy, we're going to see is only non-zero when there's an edge in my graph. This is an extremely sparse matrix. You know? And so both of these are properties that we can leverage to come up with even better linear solvers than the generic sledgehammer. Right? So we have the generic sledgehammer. We now can solve these problems, but we can do it better. Okay? So with that, I want you guys to keep thinking about that. Don't forget to take your little quiz. I'm guessing, did at least one person in this room probably took it during lecture? No? You're not brave. Okay. Well, make sure that you do that at home. I promise it won't take you very long. And with that, we will see you on Tuesday. And start your homework if you haven't. So that's due Sunday. That is due Sunday at 11:59. That's right, the quiz.